we're talking about as volume as a microservice, which is I was saying that we doing a distributed block storage solution which using a Docker. And my name is Sheng Yang. I'm currently a principal engineer at Rancher Labs. Previously, I worked at Citrix and Intel, focused on the kernel part, and the Citrix, I'm working on the cloud stack. So I want to talk a little bit about the Rancher Labs. So we're basically we are doing the container management platform, and in fact, currently the storage is not really one of the strengths, but we spot some new opportunity when we discovered that Docker can do a lot of things, probably differently from what we have done traditionally before. So we took a chance and started this project. So here is the agenda. I want to talk about the first, just give a brief ideas of what's the deal about the Docker, because we probably already heard a lot of buzz around it for the last couple of years. And since it's a storage conference, I don't know how many users are really familiar with Docker. So may I ask questions? So how many users already using Docker? Okay, about half. Okay, how many users heard about the Rancher Labs before? One. Oh, okay, that's good. That's almost equal. Okay, and later, and then I will talk about what's our traditional distributed storage cluster looks like, and we talk about the Longhorn and what's our implementation details on the Longhorn, and finally I ask out some questions. Okay, what's the deal with Docker? You probably, as in the computer or cloud computing industry, you probably heard Docker a lot for the last couple of years. And in fact, for me, it's about 10 years ago when I started my career at Intel, I already heard that, container will be the new big thing. And I remember that Google is pushing a lot of patches for the C group, and we're using container called LXC. At the time, that's a long time ago. At the time, I was starting as working on the KVM, and that's a whole story up there. But for the last, I think before the 2012, we really didn't see much activity on the follow-up for the container part until we saw what's happened with Docker. I think I got familiar with Docker about 3 years ago when I joined the Rancher Labs. At first, I think, another container technology. We already have this story before. But why is it different this time? That question has been answered very quickly, because after I tried Docker, I immediately realized that it's the change of the ways how you do the development, how you do the distribution. It's much better and much easier to use than the traditional container technology. For the Docker itself, it's basically, you can think that the Docker itself, the biggest advantage is that you have an image which is relatively small compared to what you have on the virtual machine, and that you can spin up it in a second. In fact, literally probably 1 second. And you have all the dependency of your servers in that image, and it's self-contained. You can run on any platform as long as probably as it's running on Linux. So that way make the software extremely portable. And we can create a lot of microservices use this model with self-contained containers, and we don't really need to concern about what's the environment, so what's dependency, which library I need to install, all these kind of things. That's enable us to make this microservice thing more flexible and bring us to our ideas that we can do something about this even outside the traditional container area like DevOps or the product or service production things. We think about that. Can we do something about this on the storage area? That's why we come out with this Project Longhorn. The traditional scalable storage cluster is something like a self. So you have a bunch of dedicated storage server, and they all provide storage for your storage pool. and your control panel group this whole storage service into a pool, and you have control panel also carve out this storage pool for each volume you want and provide that volume to the computing node. If you know enough about the Ceph, you can see that there's a lot of things involving that. For example, whenever you have to install on the node, you have to, in order to form one real storage pool, you have to install the monitor, which is the different process. And the monitor has to be in odd number because they have to reach a consensus if you have some conflict information from different monitors. They also develop very clever algorithm to locate that which block belong to which host, then they can track the traffic on that. They can redirect traffic to that. So that whole control panel there is taking charge of the whole storage layer, and that is one big chunk there. It's pretty complex, and it's supposed to be very efficient. But our problem is, in that case, we basically have one controller. Probably is going to form by the different process, but it's a whole thing. It's one controller. We're using one controller for 100 or even more volumes. And what if that this is something, I think, for example, a bug in that controller, you are probably going to lose that 100 volume all at the same time. That is pretty risky, and also that controller, because you have to take responsibility for 100 or even more volumes, it must be very complex to do so. And what we think about after we see the Docker and what the Docker can do, we think about that. Can we use a separate controller for each of these 100 volumes? That brings us to this question and say that we cannot do this before, because if you want to run a separate process for each volume, it will be nightmare to schedule. You don't really schedule the single process across the different hosts. That's not something you can do. They have so many dependency issues, package issues, all these kind of things. But after Docker, we have ability to manage these controllers and all these small microservices. Because Docker provides a way for you to package this thing into separated, schedulable small components, microservices, and we can schedule this thing and make it possible. Okay. So here is the overall. I think this thing goes faster than I do. Okay. All right. Here's the overview of the Longhorn. You can see on the bottom there's the two hosts with the storage, also computing. Now I think I'm going to use now we create one container. Now we create one container with Docker volume driver. The Docker volume driver is basically one persistent storage connected to a Docker container and the persistent state of that container. And when you see the container one, the Docker volume was created, we are going to do two different things. First, we'll create two replicas. Let me see. If you can see that, we'll create the replica, this replica, and this replica. They exist on the different hosts. We do that just to make sure that you have failure recovery if one of the hosts is down. Then we create a controller. There's one controller per volume, and we connect the controller to the replica. So the controller will expose an endpoint as the Linux block device to the container, and the Docker driver can do whatever they want after, and connect to that block device into the Docker container. In fact, here it's not only because the endpoint of our Longhorn system is a block device, so you can use that even without the container. You can use that like whatever you use with the Amazon EBS. It's just a block device. And when you create a second volume, when you create a second container or whatever virtual machine or whatever, you can see that we create another controller with two replicas on the two different hosts. And the third one is the same. So you can see that the replicas, they can share the same hard drive or different hard drive. We didn't really care. In the backend, the format saved that is we call differentiation disk, which is basically the file with basically the raw file on the local file system. So that's why that is the basic concept of how Longhorn works. Compared to what we have seen before on the Ceph or other distributed storage system, we think this one is pretty simple and pretty easy to understand. The problem we have now will be how the middle layer, you see that there's many microservices. We need to find a way to management and orchestrate them. Luckily, Rancher is the container orchestration platform company, so that's what we do. So by this whole thing, from the Docker volume controller replica, this whole pictures is what we have right now on the Longhorn system. For the Longhorn itself, we're something we do and something we don't. We're focusing on the simplicity, reliability, and performance. You can see that, in fact, there's a priority here. We want things to be simple as possible. And the Longhorn itself is an open source project. We want people to contribute to it and use it. And I know the storage itself is normally very hard, it's very complex. In order to get more people to involve to help the project to success, so we put the simplicity as the first priority. And of course, the reliability, because we are doing the storage. The lost user's data is probably the most unforgiving thing on earth for the IT department. And finally, we have the performance. And what we do now is that for the controller, we do mirroring. Means whenever what data you write into the controller, we write that directly into the two different replicas or how many replicas you choose. Every replica has the exactly same data. What we're now doing is doing the stripping or dedupe or compress. And that part is because that we want to keep this process simple, at least for now. And also, the controller can do the rebuild. What we call the rebuild here is whenever you have a replica failing, which is probably inevitable. When you have the replica failing, we need to rebuild that replica using the same existing replica. So we can ensure that you still have the availability available after you got some failures in your host. And what we're going to do is the controller will take responsibility for the encryption of your data. This is what we haven't implemented yet, but it's on the roadmap. And for the replica part, what's the most important feature we have is the snapshot and the backup. Our snapshot mechanism is the O1 algorithm. So basically, taking snapshot literally just in the backend literally just means you rename a file and create a new empty file and point and update that. And the backup, what we do is we allow you to connect to a secondary storage to store whatever snapshot you take. And also, we are planning to support the QoS on the replica side as well. What we don't do on the controller HA, we're not planning to do that because controller always will coexisting with your for example, the container or virtual machine you are on the same host. As long as they are same host, the major disaster we are planning for is the host down. But if the host down, your computing resource already down. So it's not much we can do. Of course, we can do. Of course, if the it's only the controller itself is down, but the host is not down, we have a policy just restart it. And also, as I mentioned before, we don't have tiering right now, and we don't do stripping and dedupe and compress. This kind of feature we probably can add in the future, but it's not in the MVP product right now. Okay, so here's the website of our Longhorn project. You can find that as if you cannot read it, I think you cannot. It's a Rancher, it's GitLab/Rancher/Longhorn. It's a 100% open source project. And in fact, there's two components of it. The Longhorn itself is basically a wrapper for you to easily launch the Longhorn system. And the other two components are the Longhorn engine, which is the microservice we talk about, acting as the controller and the replicas. Another one is the Longhorn manager. A Longhorn manager is the orchestration of the middle layer you see before to decide that where to put the controller, where to put the replicas, and when I want to issue command to do the replica rebuild and the failure recovery things. The Longhorn itself is written in Go. So we take advantage of Go's synchronized programming and the channels, all these kind of features, and make it very easy to understand. Okay, so any questions so far? So here, I'm just make a brief introduce on some technology we use when writing the Longhorn. So basically, what Longhorn right now is in the back end is just a series of files, and each one is in fact a whole sparse file in the Linux. And you can see that each snapshot is a single differential disk file, as we call it, and each of this a sparse file. And the reason we are using sparse file is that we depends on the internal metadata of that sparse file to decide that where the data is. The block size is 4K, and the Linux will tell us that this part we have data in this block and that block, and we're using that metadata to form a chain. You can see that okay. So if I want to read the block 1 of this block device, I will take a look at that, see that if I can find the block 1 in the live data. And I can't find that in live data, so I just return that live data's block 1. You can see that we also have the data in the newest snapshot, the middle one, and the oldest snapshot, and the middle one. That one is not selected because the newest data is always taken the highest priority. And the next one is I want to read the block 0. I cannot find anything on the live data, so I try to look down into chain and see what the next one is. The next one is on the newest snapshot. That's why I choose it. Okay, then the block 2, you can see the block 2 is at the oldest snapshot because none of the snapshot before the oldest snapshot has the data. Now you can see the pattern. And the block 4, in fact is empty there. So that's why he reads through the oldest snapshot and returns empty. And the block 7 will be on the live data. and block 3, and 5. Okay, so this thing really doesn't work. Oh, here, you can see that we write a new data in the block 5. Originally, block 5 is reading on the middle snapshot, but after we write into the newest live data, we're going to change that index to point to the live data. So that's why that's how we have the read index always updated and find the fastest way to read the data we want. This is about the reading, and for the writing, it's always easy because the live data always have the highest priority. So whenever we want to write one block into the system, we just write to the live data, and we update the reading index accordingly. So this is how we implement the snapshot internally. Here I talk briefly about the backup. I remember at CloudStack when we do the backup for the Zen server, we always have that problem that because the Zen server also using differentiate disk and as a chain, but there's a limitation on that chain. I remember the depth of the chain must be less or equal than 7, which is pretty shallow if you consider that you're probably going to make a backup once a day or once a week. So at the most after 2 months, you have to do the coalescing, which is basically merge two snapshots together, and in order to get a longer chain for you, get a new room for the snapshot. That's why it's really I/O intense operation. So after that, we're thinking about a new way, which is we think is better. And what we're doing here is that we call it the change block mechanism. What the change block means, you can see that we want to store the 2 snapshots into secondary storage, the snapshot 2 and snapshot 3. The snapshot 2, they have only 2 blocks. With the snapshot 2 itself has only 2 blocks with green color. And of course, when you say snapshot 2, you want to have the content of snapshot 1 as well, because that is the ancestor of the snapshot 2. So you want to have the data at the moment snapshot 2 is taken. You will have the data of snapshot 2 plus all his ancestor. So you can see that the snapshot 2, basically snapshot 2 is the index. It's pointing to 2 green blocks, and 1 gray box. So that was how snapshot 2 was made. Now take a look at the snapshot 3. You can notice that the snapshot 3 has 2 blocks additional to the snapshot 2, but one of them, the second block, is overlapping with snapshot 2. So you can see that on the snapshot 3, what we save is the first block is pointing to a new block. The second block of snapshot 2 is also pointing to a new block. It's because the snapshot 3 is the second block of snapshot 3 is also pointing to the new block. Because the snapshot 3's block override what happened in snapshot 2. But the remaining thing, you can say the block 3 of snapshot 3 is a point to the exactly same block as snapshot 2, and also the block of snapshot 6. That's because when we create the snapshot 3, what we have is we are copying whatever in the snapshot 2, and also we calculate that what is different between the snapshot 2 and snapshot 3 using the reader index before. We mentioned just on the last slide. So after we know the difference, we only copy and overwrite the difference and keep the same part of storage as the same with the snapshot 2. In that way, each snapshot we have is the whole data. And if you want to delete the snapshot 2, it's almost no cost because we only delete the index. we have a built-in garbage collection mechanism after you do any of the deletion. So after you delete snapshot 2, we're going to scan every blocks and find out which block is no longer being used, and we clean up that up. And here we're choosing the 2 megabytes block size, but that is configurable. So by this way, we no longer depends on what the chain is to perform this snapshot backup and restore operations. And we don't have the limitation. We don't limit it by how big the chain is as well. And we don't need to work down to chain to find out which is the right blocks. Basically, we just paid price up in the front in the backup, and don't pay it later. Then here is how backups are stored. So for the backup, you can see that we have basically separate what is backup and what is blocks. The blocks is here is we did a checksum of the block and uncompress them. And for the snapshot 2 establish3.conf, the backups only have to say that which location is this block and what the block is. This kind of information, which is very straightforward. And also this, you have some potential dedo by itself if their same blocks happens in the same volume. For example, if that block is O0, it can be, we only store one copy of that in the second storage, because we just decided what the block is by the checksum. And here we're talking about, say, replica rebuild. So essentially this one, when you have the replica down, or you want to add a new replica in addition to the current replicas, you got to do this. The process here is first, you can see that we have live data snapshot in the existing replicas. The first, we are going to pause the controller very, very briefly during the time there's no read or write allowed. And then we take a snapshot of existing replica. You remember that I mentioned that because we are only, this take snapshot action is O1 operation. It's very fast. We basically just rename the name of live data and create a new snapshot of that. I basically rename that to a new snapshot name and create a new empty file of the live data, and we update our chain to point the header into the live data. It's pretty fast. And the second thing we do is we add a new replica into write-only mode. Because at this time, the live data of the existing replica and the new replica are both empty. We just created that. So the new replica can execute whatever write command from the controller. But the reason why is write-only because we have no existing data in the new replica. So of course we cannot read from it. So then we unpause the controller. And finally we sync up, finally we sync up the snapshots. We start another thread to sync up the snapshot with the new replica from the existing replicas. This is basically a fancy rsync process we have. And we write it to ourselves because we have to preserve the metadata of the sparse files. After we complete the syncing, we set a new replica to read-write. And now new replica is as good as the old one because any new data writing into the new replica will be landed in live data at the same time as the existing replicas. And also the snapshot of the new replica had just been copied from the old one. So they are exactly the same. This process is probably the most complicated process in the Longhorn, but it's still pretty simple. The live update is what we want to do in the future. Currently, because we are taking advantage that we have a loose couple between our front end and our controller. In fact, we spent quite an effort in search for the perfect front end for the Longhorn, because at first we are using the NDB, and we realized that this NDB has a very big issue when the connection was disconnected unexpectedly. It can easily cause kernel panic. And I was told that this was fixed about a couple months ago, but we don't want to adapt the new kernel as the same reason as we using why we change it to TGT rather than the TCMU. Okay, the story about TCMU is that after NDB, we try to find a new, the faster way to expose a block device in the Linux kernel. And I wrote some patch on the TCMU to increase the performance and add or synchronize the I/O into the TCMU. But later we realized that if we are forcing everyone to use in TCMU, they have to run the kernel probably newer than 4.5 or 4.6, which can be a big hurdle for the new project like this, and people probably just don't want to do that. So finally, we think we can sacrifice the trading performance a bit, try to get a better compatibility by using the TGT, which is the user space iSCSI target. So I wrote some code as a new iSCSI target for TGT and connect it to the controller. The TGT support has been in since 2621 or 2618, which is years ago. So we don't really care. We don't really worry about the compatibility for the user. And in the end, we found that performance a little bit worse, but not too bad. So we accept it. And during the time, we also try another solution using the Fuse. It's just a user space file system driver in the Linux kernel. And we wrote a driver for that, and found the Fuse is really too slow for us to tolerate. So we give that as well. But in the end, we have a solution that's on the front end part is basically an iSCSI target. It doesn't matter if it's TCMU or TGT, it's the iSCSI target. And the controller will issue the iSCSI command to connect to iSCSI target. So they give us a way to do the live upgrade because they are loose coupled. Whenever I want to have a new version of Longhorn deployed, what I want to do is I just start a new version of the controller and the replicas and point to the same data we have, of course with pausing the control and then pausing the controller, and I just switch over. Because that's just a matter of changing iSCSI target. This is something we haven't done yet, but it's on our roadmap. For the Longhorn, we have two deploying models in mind. One is called the hyperconvergent infrastructure, which means you mix your storage and your computing node at the same machine. Another one, we can also support dedicated storage service. And the second model, we will have the replica running on this dedicated storage service and the controller running on the computing node. They connect by the high-speed network. So what is working right now? Longhorn is still in the fairly early stage. And currently, we can do the distributed volumes on a Docker Swarm cluster. And the failure detection and replica rebuild are done, and snapshot backup. And also, we support scheduled snapshot and backup using Chrome or similar things. And also, we have a Longhorn dedicated UI, a pretty simple one, and also the API. Now, this list is much longer. The first in our mind is we got to support the Kubernetes Flex volume driver, which is still not there. And we need to, as a rancher, our company's major product is still rancher. So we need to deploy Longhorn cluster from rancher catalog, and live upgrade, and the event logs in case of something goes wrong. and the ability to backup to S3. Now we support the backup to the NFS only, but the code is there for S3. I basically moved that code from my old project, Convoy, so that's somehow still useful. And we need to advance the scheduling based on the disk capacity and I/O ops, and multi-disk support, volume stats, authentication, encryption, and finally, we'll look at performance. Yeah, I think that's about it. Any questions? Sorry? Yeah, the replica controllers, they're both Docker containers. We built, that's part we call it Longhorn engine. So the Longhorn engine can be started as a controller and or as a replicas. And because we use the Docker, so we basically build this kind of microservice, we can easily schedule across the host. Yeah, and even the Longhorn manager itself is the containers. Just think about the container as a kind of service, rather than now say it's not really very different from others. It's just the format of how we distribute this, but because of the Docker, it's possible for us to distribute the Longhorn engine, this replica and controller container easily. That's it. Yeah, if you want to have more replicas, you can just add the scale, and we'll add a new replica into that. We just add a new container to another schedule to another host, connecting the controller. The same process as we do the replica rebuild.
So you said that you were considering TCMU and then you were using PGT instead, right? For various reasons. So TCMU is like kernel, and the other is completely user space, is what you're saying, right?
Okay. The TCMU is called the TCM user space, and the TCM is the currently Linux kernel SDC target framework. And the reason we want that is with the performance of TCMU is after we enhance this, it's pretty good compared to the TGT, but still the user have to have new enough kernel to use this, so we switch to the TGT. Yeah. Yeah, in fact, currently we're using ext4, but I think as long as the file system do the right thing with sparse file, we can use it. All right. Okay, I think that's about it. Thank you.